This is the Harman Kardon PM645 amplifier. There's something wrong with it, but I don't know what right now, but we'll find out. Okay, I have the speakers connected. Let's power it up and see what happens. It does turn on. There's some bad connections in the switches to start with. Okay, it sounds like some really bad misconnection somewhere. Maybe a cracked solder joint or something. Let's open it up and see what it looks like. Okay, so let's try to figure out what different parts of the circuit does. I did find the service manual and it seems to be a quite nicely written one. The scan, on the other hand, that I found is not that good. It lacks some information. Here it's supposed to say voltages, which would be very nice information, but it is more or less completely gone, that text. Here we have the input RCA connectors. It's these here on the back. We have the equalizer. It seems to be this PCB here, and it's used for the phono input. I'm guessing this is what is usually called a Aria amplifier. So the phono input goes to the equalizer and then continues to the switchboard. And the other input signals go straight to the switchboard. Then we have the pre-driver, power driver, tone control and power supply. That seems to all be on the main PCB. Then we have this circuit that seems to be the base contour circuit. So what is base contour? I'm reading from the manual. The switch activates a unique low frequency equalization circuit that provides full, natural sound from small speakers that are normally deficient in the bass region. It also says that unlike conventional bass boost circuits, Harman Kardon's base contour includes a phase correction circuit that maintains clear and natural sound. So the idea is to feed a signal to the input and then search for that signal all through the amplifier and see where it starts to disappear. Let's feed the amplifier with a 440 Hz sine wave with a signal level of -10 dBV, which is the consumer standard. A lot of the initial signal processing is done passively, so we can start searching for the signal before we turn on the device. Here is right at the input, the left channel. Here is the right channel. I'm feeding the right channel with a triangle wave instead, so we can separate the two. Here we have the inputs to the switchboard. Here we have the output of the first switch. Then we have a switch for the tape monitor as well, but we'll ignore that for now. So after the switchboard, the signal goes to the high cut and the subsonic filters, which are located on this PCB. Right input. Left input. By the high cut filter. Does not have any effect on the signal as it's quite low frequency. Then we have the subsonic cut filter. Here we have the output. Has some effect. Let's check the left channel. It's still there. Then we have the mode selector switch. It is located on the main PCB underneath this, so we'll skip that for now and move along. We have the balancer that is also located on the main board. Then we have the volume control, which is located right here. The left channel seems to be gone. If I change the mode to mono, it appears. It doesn't help to reverse. So here we have the different modes of the switch. In the stereo case, the left channel goes to the left signal processing and the right channel goes to the right signal processing. In the reverse mode, the left channel goes to the right signal processing and the right channel goes to the left signal processing. In the mono case, left and right channel are connected together. So since we get a signal here in the mono case only, it seems like this part is working, which means that there's probably something wrong with the mode selector switch. But just to make sure, let's see if the balancer works as it should. It works as it should for the left channel. The balance circuit works for the right channel as well. Okay, so there's probably something wrong with the mode selector switch. Let's take a look at that. It's very nice that they made it so easy to access the PCB from underneath. Here we have the balancer. Here we have the left channel. Here we have the right channel. Here we should have a sine wave, but we don't. So it's probably something wrong with this switch. I see here if I tilt the switch a bit, the sine wave appears. All the joints have been resoldered. Let's measure it again. The right channel is there just like before. And the left channel too. Yep, it's there now. So it seems like it was a cracked solder joint after all. Now when we're down here, look at this star ground. Beautiful design. So this layout design is a way to make the signal processing sections less susceptible to noise on the ground. And that is because everything in this section relates to the same point in the ground, which means that if there's noise on this ground, so that it moves up and down in voltage, everything in this section will move up and down simultaneously. So there will be no voltage differences, and you will not introduce any more noise in the signal. Okay, let's see if that solved the problem. Interestingly enough, we get audio on the left channel only now, so there's still some work to be done. I'll notice that this power supply section is not looking very nice. Let's take a closer look at that. Well, this is absolutely horrendous work. Look at this. This component is completely loose. And there are a bunch of other very questionable solder joints across this power supply section. Well, that needs to be fixed. So I had to scrape some other part of the trace to get to the copper, so the solder has something to stick to. It's not pretty, but it's a lot better. Okay, let's test it again. Ah, now the bass contour is working. We still get sound only on the left speaker, but now the bass contour is working. So the power supply seems to be divided into two sections, and the bottom section here is the one that supplies the base contour circuit. So I guess this is where we saw the bad soldering job that we fixed. Okay, let's continue where we left off. We should have both left and right channel before the volume knob. The right channel and the left channel. Let's see, after the volume knob, let's turn it off. Right channel, left channel. Alright. So after the volume control, the signal goes to the base contour switch, which is this one. And here we have the output of the base contour, whether or not it's bypassed or not. So there we should have a signal while the base contour is off. There we have the left channel, base contour on, base contour off. There we have the right channel, base contour off, base contour on. So that is as it should. Let's see where the signal goes next. The signal then continues to the pre-driver and then to the power driver. So I'm going to start by measuring the output of the pre-driver right away to see if there's an error in the pre-driver or if it's in the power driver. So we're going to measure on the output of the pre-driver here. For this part we're going to have to turn it on. On the output of the left pre-driver we have a quite clear amplified signal. Let's look at the right channel. Not much there. So I'm guessing there's something wrong in the pre-driver. Let's remove the base contour board so we can see what's going on underneath. Okay, let's start from the beginning. Here we have the input of the preamplifier, here and here. Let's see if we have signal there. So there's signal on the input of the pre-driver. Here we have the first amplification stage, so let's look at the output of that stage. We have nothing. So there's definitely something wrong in the first amplifier stage. Let's take a look at the components around the first amplification stage. We start by looking for shorts in the first stage. Seem to be working. Let's take a look at the following stages. They seem to be working. Let's measure the voltages on the transistors to make sure they're biased correctly. And here in the schematic we have what appears to be the leftovers of bias voltage values. And these would be really nice to have right now, because if we measure the voltage on this node and it does not match with the voltage value indicated in the schematic, we know that something's wrong. Now the good news is that it's a stereo amplifier, so we can compare the values of the working left channel with the broken right channel. Let's start by measuring the collector of the first transistor on the working channel. There we have almost 40 volts. So that's what it should be. Let's look at the broken channel. -1 volt. Okay, so there's something wrong. Okay, let's look at the positive rail. That should be 40 volts. It's 0 volt. The rail voltage seemed to go through this component. So there's voltage on the positive rail. This node is shared between the two stages. So the voltage should be passing through this component, but it doesn't. So it might be something wrong with this component, whatever it is. Let's take a look on the other side. As it appears, it was two components. It was these two resistors here. Let's have a closer look. This one and this one. And it's these two resistors located in series with the positive voltage rail. So they should both measure 10 ohms. 10 ohms. The other one is just behaving weirdly. It needs to be replaced. We can see that in the schematic this resistor has a small warning triangle above it. Apparently that means that due to safety requirements these components must only be replaced by original parts. So if we look at the parts list, we have the resistor here, and it says that it's 10 ohms plus minus 2% quarter watts fuse. Okay, so apparently this resistor is used as a fuse. So it's important that the replacement resistor does not exceed this power rating, as it's supposed to blow when you draw too much current through it. So here we have what I believe is a suitable replacement resistor. It is definitely a quarter watt resistor given its size. It does not have a 2% tolerance, but I can measure this specific resistor and conclude that it's within the tolerances. Alright, let's replace it. Alright, let's see if that's it. Apparently not. At least the resistor seemed to work as a fuse. That's nice. Given how fast it blew, there must be a dead short somewhere in the pre-driver circuit. Let's see if we can find it. There's a dead short between the voltage rail and ground. No wonder it blew fast. The only obvious direct connection between the power rail and the ground is through this decoupling capacitor here. Let's desolder it and see if the capacitor has gone bad. Yep, it's bad. When you see a blown fuse, you should try to figure out why it blew before replacing it. My mistake. Now, I was a bit surprised to find that it was caused by a dead short, because this is not what I expect a resistor fuse to look like when it's blown by a dead short. This is. So it could be that the capacitor started to go bad and the resistor fuse blew, and then after that the deterioration process of the capacitor continued and caused it to short completely. Let's get rid of the new blown resistor fuse. We'll replace the capacitor with this surface mount one. So we will have to bend the legs. And remove the plastic part. So let's make sure the positive voltage is not shorted anymore. No smoke this time. Everything seems to be working. Nice.